Good afternoon, everyone. Does everyone have the handout for today's class? All right, let's go ahead and get started then. Today we're going to start a new topic, mechanical properties, and we're going to start with the concepts of stress and strain, and we'll learn a little bit about the tensile test. So by the end of today's lecture, you should be able to define the concepts of stress and strain, be able to calculate those values. You'll learn about Hooke's law, and you'll be able to use that to relate the concepts of stress and strain to each other, and you will be able to identify some of the key features on a tensile, on a stress-strain curve, which is generated from a tensile test. So why do we care about stress and strain? As engineers, everything we build experiences forces, pushes and pulls in different directions. So as a biomedical engineer, you might care about the forces on your ligaments or muscles or bones that you're trying to model. Or if you're developing sutures, you'll want to know about what the material of the suture, how it undergoes those forces. If you're a civil engineer, you're building buildings. You want to know about bridges. How many cars can you pass over a bridge? How tall can the building go? You need to understand the material properties and the stress and strain felt in those materials. Or in mechanical engineering or aerospace, when you're building airplanes, cars, trains, or elevator cables, anything like that. And how do we measure a stress and strain? We use something called a tensile test. In a tensile test, we pull on a specimen. This video is a demonstration from Instron, who makes tensile tests. So here they're going through and showing you some of their instrument. So I'm going to pause it right here, but here you can see this is a top clamp and a bottom clamp holding the sample, the specimen. They'll zoom in and we can see that. So as soon as the worker hits start, the clamps will move in opposite directions, applying a pulling force in one direction on the sample. We'll come around the corner, and here you can see the live data generation, and you can see the specimen as it's pulled. So here you can't quite see the axes here, but we'll look at this later. This measures the elongation of this gauge length here versus the force that's being applied vertically. Tensile tests give us a lot of data, and they're typically done until fracture, as you can see at the end of the test here. We can get lots of things out of a tensile test, such as the elastic modulus, the fracture strength, the elongation, the ductility, the ultimate tensile strength. We'll talk about most of those in another lecture, but we will touch on a few today. So here is a generic stress-strain curve. So those axes of elongation and force can be converted to stress and strain. Stress on the y-axis and strain on the x-axis. And as you can see, there are a number of different features on this curve that we'll talk about. First off is stress. Stress is defined as the force applied to a material over its cross-sectional area. And we want the area that is perpendicular to which the force is being applied. By dividing by the cross-sectional area, we're able to normalize the force and compare between different geometries and different materials and different samples. So I'll have you all do example 1 on your worksheets there. Given this rectangular specimen, if I pull on it tensily in its longitudinal direction with a force of 25 newtons, what is the stress undergone? Yes?
25 kilopascal.
Exactly. That is exactly right. And so we calculate that by using this cross-sectional area of 5 centimeters by 2 centimeters. It gives us 25 kilopascals. Now, one of the biggest common mistakes when calculating stress is to use the incorrect cross-sectional area. Again, we want to remember that it's the one perpendicular to which the force is being applied. If I change the cross-sectional area, or if I change the direction in which the force is being applied, we'll change the cross-sectional area. So does anyone know which cross-sectional area we'd use here? Yes?
So I think it is 5 kilopascals?
Yes, That's the correct answer. And we'll use the cross-sectional area that is 10 centimeters by 2 centimeters. Nice job. So now moving on to strain. Strain measures the deformation longitudinally in the specimen. So we define that as the change in length over the initial length. So over here on the left, we have our initial sample, and we apply a force to a specimen of a known length. After that force has been applied for a certain amount of time, the length of the specimen will change. And we calculate the change in length as that final length minus the initial length, and that divided by the cross-sectional area is our strain. So now you might be saying to me, well, it seems like this is pretty independent of material. It only depends on what the specimen itself looks like. Well, that's where the elastic modulus comes in. And if we can relate the concepts of stress and strain to each other, that's where our material property comes in. So looking back here, our Young's modulus is defined as the rise over run, or the slope of the linear portion on the stress-strain curve. We use Hooke's law to relate those two. So this is our y-axis, strain is our x-axis, and you're multiplying by a constant, the Young's modulus, to get the relationship. So I have one more example for you here today. Now, using Hooke's law, what is the strain undergone by this material? The same dimensions as the specimen before, same force. Yes?
I got 0.125 times 10 to the power minus 6.
Yes, that is correct. So we're using this cross-sectional area that is perpendicular to the force being applied, much as we did in example 1. And then Hooke's law is the stress, 25 kilopascals, divided by the elastic modulus, which is 200 pascals here. So going over what we've learned today, we've only covered a small portion of a stress-strain curve, but we do see that we learn the definition of stress. We see where that is on the stress-strain curve. We know strain, and we learned our elastic modulus. So next time we'll talk about the yield strength and the ultimate tensile strength.